Okay, so for the last few weeks, we've been talking about the structure of the atom, and we trace the word atom all the way back to Democritus, all up through a number of scientists, to some of the more recent models of the atom, like Thomson's, Rutherford's, Bohr's, which then led us into quantum. Through all of it, with the exception of a little blurb on Rutherford's, we haven't talked about the nucleus at all. And we've spent a lot of time with what are the electrons doing, knowing that the nucleus was holding them in there. And Rutherford's the guy, remember, with his alpha particle scattering experiment, that figured out that in the center of the atom, there is this massive positive charge around which the electrons are moving. And he knows it's positive because Rutherford figured it was positive because he was shooting positive alpha particles at it and they were reflecting back. We know it's positive as well because it's holding the electrons in there. Rutherford figured it had to be massive because of the way the alpha particles were sent back out, the ones that came close to it. So in this unit, we're going to move away from looking at what are the electrons doing, and we're going to look at what's happening inside the nucleus. So this unit is called, I think in your notes, I called it nuclear energy. I would probably really call it nuclear physics because I'm a physicist, but if there was a chemist teaching it, they might call it nuclear chemistry. It's one of those units that appears in both subjects in university, and so you'll notice at the top of my page, I just called it nuclear, to be safe and keep everybody happy. And so what is it focusing on? It is focusing on, of course, the nucleus. And so we know the nucleus is the core of the atom. We know it's the concentration of positive charge, and we know it's the concentration of mass. Through time, though, we figured out there's more than just positive charge in the nucleus. There are also neutral charges. So inside the nucleus, we have particles that we call nucleons. And you may or may not have heard of this word. And nucleons really include two things. They include the protons, and they also include the neutrons. So the protons are the positive elementary charge, so their charge is 1.602 times 10 to the negative 19 coulombs, just like an electron's, and except that theirs are positives and electrons are negative. And protons have a mass of 1.673 times 10 to the negative 27 kilograms. So they're much, much, much heavier than an electron. Compared to an electron, a proton is massive. Now, it might not seem that way to you because negative 27 is pretty tiny, but remember an electron is negative 31. So the proton is like somewhere between 500 and 1,000, more than 1,000 times heavier. Okay? A neutron is neutral. Okay? So no charge on a neutron. Its mass is 1.675 times 10 to the negative 27 kilograms. So some people would say they have the same mass, but really a neutron is slightly heavier than a proton. And they both make up the nucleus, okay? Or both are found inside the nucleus. The number of protons in a nucleus is what determines what element you have, but the number of neutrons for a given element can vary. I think in chemistry you would have met the atomic number. And we've actually used it. We used it when we were doing our electron configurations in the last unit. The atomic number is simply the number of protons an atom has. Okay? And if an atom loses a proton, it's no longer the same atom. The atomic number is the SED. And I was using it last unit when we were saying, okay, sodium is SED equals 11. So it's telling us the number of protons. If the atom is neutral, then it's also the number of electrons. But we know that electrons can be removed from atoms, so we always define the atomic number as the number of protons, because protons cannot easily be removed from an atom. Okay? So each element has a different number of protons. So each element has a different set. Why am I writing this down? I guess so you can. And therefore, each element has a different atomic number. And if you look at our periodic table, then you'll notice that the elements are listed by their atomic number. If the atom is neutral, the number of electrons will equal the number of protons, will equal the atomic number. But this part does not always have to stay. The number of protons is always the atomic number. The number of electrons is not necessarily. There's another number that I'm not as sure that you would have met in chemistry, and it's called the mass number. Now, unfortunately, its symbol is A. I didn't make it up. I know that A would make a lot more sense to go with the atomic number than it does with the mass number, but I think Z was already with the atomic number. The mass number is the number of protons plus the number of neutrons in a nucleus. In other words, it's the number of, our new word up here, it's the number of nucleons. Okay? The mass number will always be equal to or greater than the atomic number. It can never be less than. But it could be equal to. In the hydrogen atom is the only atom that doesn't, in some of its isotopes, doesn't have a neutron. And so then the mass number and the atomic number would be equal. If you want to get the number of neutrons, then it would simply be A minus Z would equal the number of neutrons. Okay? Because this is the number of protons plus neutrons minus the number of protons. Now, we have a way to write all of our elements so that we can see exactly how many protons and how many neutrons it is. So if this is the symbol of the element, then the top number is our A, is our mass number, and the bottom number is our atomic number, is the Z. So the top number is always the bigger number. So what I just said to you was hydrogen. The most common isotope of hydrogen is 1,1. So it has 1 proton and 0 neutrons. Helium, we would write it as 4,2. So 4 nucleons, 2 protons, 2 neutrons. Now the number of protons and the number of neutrons do not always need to match. Carbon-14 is a common isotope of carbon. And so it has 6 protons and it would have 8 neutrons. So the number of protons has to stay the same for a given element, but the number of neutrons doesn't. And because of that, it leads us to something called isotopes, which I think you would have also seen in physics and chemistry, but we'll get to them in a minute. First, though, going back to the way we write our elements, we can also write our subatomic particles like this. So an electron, which is an E, we would write as 0 because it has no protons and no neutrons, and -1. So it's like -1 because it's the same as a proton, only negative. Our proton would be P11, but you will also see it often as H11. If it's inside the nucleus, we'll usually write it as a 11P, but if it's being released, if it's outside, then we would write it as a 11H. It's like a hydrogen atom. And then our neutron was an N. Its mass number would be 1 because it has 1 neutron, and its atomic number would be 0. Okay, so these are important. We'll be using these throughout the unit